Hello everyone, welcome to my class. This is mathematics class for class 10 students. We will continue with our first chapter, real numbers. Today let us start with the question given here. Use Euclid's division lemma to show that square of any positive integer is either of the form 3m or 3m plus 1 for some integer m. We have already discussed Euclid's division lemma, so you all know what is Euclid's division lemma, so we will use it here. Let a be any positive integer and b is equal to 3. By Euclid division lemma, a is equal to 3q plus r, then r will be equal to 0, 1 or 2. So we get a equals to 3q or a equals to 3q plus 1 or a is equal to 3q plus 2. So we have three cases here. We will start with case 1, that is a is equal to 3q. Squaring both sides, we will get a square equals to 3q whole square, then a square is equal to 9q square. Then in the next step, we will take 3 common, so we will get a square equals to 3 in bracket 3q square, or we can write it as a square equals to 3m, where m is equal to 3q square. Now let us see case 2, where a is equal to 3q plus 1. Again squaring both sides here, a square is equal to 3q plus 1 whole square. Then using a plus b whole square formula here, we will get a square equals to 9q square plus 6q plus 1, or a square equals to 3 in bracket 3q square plus 2q plus 1. Here we have taken 3 common from the two terms, that is 9q square and 6q square. Or we can write it in the form a square is equal to 3m plus 1, where m is equal to 3q square plus 2q. Now let's see the third case. A is equal to 3q plus 2. Squaring both sides, a square is equal to 3q plus 2 whole square. Using a plus b whole square formula, we will get a square is equal to 9q square plus 12q plus 4, or a square is equal to 9q square plus 12q plus 3 plus 1. Here we have expanded 4 as 3 plus 1. So in the next step, we can take 3 common from 9q square, 12q and 3. So we get a square is equal to 3 in bracket 3q square plus 4q plus 1 outside bracket, or a square is equal to 3m plus 1, where m is equal to 3q square plus 4q plus 1. So what we observe here is that in case 1 we got a square is equal to 3m, in case 2 we got a square is equal to 3m plus 1, and in case 3 we got a square is equal to 3m plus 1. So we can say that square of any positive integer is either of the form 3m or 3m plus 1. Now let us discuss the next question. Use Euclid's division lemma to show that cube of any positive integer is of the form 9m, 9m plus 1 or 9m plus 8. Now let us see the solution. As we know that Euclid division lemma says a is equal to bq plus r. So let a be any positive integer and b is equal to 3. By Euclid division lemma, a is equal to 3q plus r, where r will be 0, 1 or 2. So a is equal to 3q, or a is equal to 3q plus 1, or a will be equal to 3q plus 2. So like previous question, here also we have got 3 cases. One point to be noted here is that we have to prove that cube of any positive integer is of the form 9m, 9m plus 1. So why we have not taken b is equal to 9 here? This is because if we take b is equal to 9, then we will get 9 cases to show there. So that will be time taking. That's why we have taken b is equal to 3 only here. So we have got 3 cases. So let us discuss case 1. So here a is equal to 3q. Then taking cube on both sides, we get a cube is equal to 3q whole cube, or a cube equals to 27q cube. Taking 9 common from this, we get a cube equals to 9 3q cube in bracket, or a cube is equal to 9m, where m is equal to 3q cube. Here m is any positive integer. Now case 2, a is equal to 3q plus 1. So taking cube on both sides, a cube is equal to 3q plus 1 whole cube. So now we will use the formula of a plus b whole cube, that is equal to a cube plus b cube plus 3ab in bracket a plus b. So we will get a cube equals to 27q cube plus 1 plus 27q square plus 9q. In the next step we will arrange it in the descending order of the exponent. So we get a cube equals to 27q cube plus 27q square plus 9q plus 1. Now taking 9 common, we get a cube equals to 9 in bracket 3q cube plus 3q square plus q bracket close plus 1. Then we can write it in the form as given here. A cube equals to 9m plus 1, where m is equal to 3q cube plus 3q square plus q. In case 3 we have a is equal to 3q plus 2. Taking cube on both sides, a cube equals to 3q plus 2 whole cube. Again taking formula of a plus b whole cube here, that is equal to a cube plus b cube plus 3ab in bracket a plus b, which can be written as a cube plus b cube plus 3a square b plus 3ab square. So we get a cube is equal to 27q cube plus 8 plus 54q square plus 36q. Now arranging it in the decreasing order of the exponent, we get a cube equals to 27q cube plus 54q square plus 36q plus 8. Now taking 9 common, we get a cube equals to 9 in bracket 3q cube plus 6q square plus 4q bracket close plus 8. So it can be written in the form a cube equals to 9m plus 8, where m is equal to 3q cube plus 6q square plus 4q. So we observe here that in case 1 a cube is equal to 9m, in case 2 a cube is equal to 9m plus 1, and in case 3 a cube is equal to 9m plus 8. So we can say that cube of any positive integer is of the form 9m, 9m plus 1 or 9m plus 8. Now we have theorem 1.2, fundamental theorem of arithmetic. Let us see what does this theorem say. Every composite number can be expressed or factorized as a product of primes, and this factorization is unique apart from the order in which the prime factors occur. We already know how to do prime factorization of any number. So let us see one example here. 24 is equal to 2 multiplied by 2 multiplied by 2 multiplied by 3. So what fundamental theorem of arithmetic says? It says that this factorization is unique apart from the order in which the prime factors occur. That means these factors are unique, but it can be written in different order also, as in the next step that is given 24 is equal to 3 into 2 into 2 into 2, or we can write it as 24 equals to 2 to the power 3 into 3, or 3 into 2 to the power 3. Now let us discuss one question based on the theorem. Check whether 4 to the power m can end with the digit 0 for any natural number m. Let us solve this question. For a number to end with the digit 0, it should have the factors 2 and 5 both. Here the given number is 4 to the power m. 4 can be written as 2 to the power 2. So 4 to the power m is equal to 2 to the power 2m. By fundamental theorem of arithmetic, this factorization is unique. That means 4 to the power m will have factor 2 only. So it has only 2 as factor but not 5. Therefore 4 to the power m will not end with the digit 0. Next topic is finding LCM and HCF of the given numbers. We have already studied how to find the LCM and HCF of the given numbers. Let us have a revision here. HCF or highest common factor is a product of the smallest power of each common prime factor in the number. Let us discuss one example of HCF. Let us find HCF of 48 and 56. Factorizing 48, we get 48 is equal to 2 to the power 4 into 3. Factorizing 56, we get 2 to the power 3 into 7. So HCF of 48 and 56, we need to see here that the product of smallest power of each common prime factor. So common prime factor is here 2 and smallest power is 2 to the power 3. So the HCF is 2 to the power 3 here, which is equal to 8. Now LCM or lowest common multiple is a product of the greatest power of each prime factor involved in the numbers. Let us see the LCM of the same two numbers 48 and 56. So here we have to find the product of the greatest power of each prime factors in the numbers. So here what we see that we have to get all the prime factors involved in both the numbers with the greatest power. So the LCM will become 2 to the power 4 multiplied by 3 multiplied by 7. Also we have one formula to verify the LCM and HCF of the given two numbers, that is LCM into HCF is equal to product of two numbers. Using this formula we can solve some of the questions also. Now I am giving you some home assignment. Solve exercise 1.1 and 1.2 of NCERT textbook. Thank you everyone for attending the class. Now we will meet in another class.